Okay, now that we have derived conservation of mass for an infinitesimal control volume to arrive at a governing differential equation, and we've run over the substantial derivative or the acceleration of a fluid, we are ready to discuss the Navier Stokes equations. I'm not going to go through them in great detail. You can learn more about them than you ever wanted to in grad school. And really, they are the governing equations of fluid mechanics. They do have some they have some interest to the general public. There are some movies made about them, and in fact, one of the $1 million math prizes is for proving the existence and uniqueness of the Navier Stokes equations, or providing a scenario where there is no solution to the Navier Stokes equations. So they are still very interesting equations, and they're used a lot. Actually, solving these Navier Stokes equations is a multi-billion-dollar industry per year. And so how these are derived are either from the Gauss divergence theorem, like I might have showed with conservation of mass, or you can derive them from an infinitesimal control volume, like I did in here, but instead of using conservation of mass, you use conservation of momentum for a control volume. And here, this is just the accumulation of momentum in the control volume, the net flow of momentum with the fluid out. This is the pressure forces acting on the control volume. This is the shear stress forces acting on the control volume. Note, this here is a tensor, and a tensor dotted with a vector gives you another vector. And we also have the body force terms, which we're just going to include gravity. And of course, because I don't have Vxyz here, I have V. This is for a stationary control volume, and it's non-accelerating because I don't have the acceleration portion. I'm not too aware of any applications where the Navier Stokes equations have an acceleration term, unless you're doing geophysical fluid dynamics, where you're actually solving the Navier Stokes equations to simulate the flow over the entire Earth, which is done, like to model hurricanes and things like that. There, they'll have Coriolis terms to account for the spinning of the Earth. But in general, us as engineers, we don't usually have to worry about those terms. Okay, and so I'm not going to go through this in great detail, but I will show the control volumes and the free body diagram. So here, like I did in everything else, we have just dp dt, which is representative of these terms here, and the sum of forces, which is representative of these terms here. And the control volume is going to be a mess, and this is in 2D, and the free body diagram is also a gigantic mess, because on the free body diagram, we have the pressure forces pushing down on it. We have the shear stress, we have the stress forces, and recall that stress is a tensor. So we have a normal component on the x-face, and we have a shearing component, and we have a normal and shear component on every single face. So essentially, we have all of these different terms here that we need to worry about. And we have the body force term, and that's just rho gv, or rho g delta x delta y, because our control volume is of width delta x and of height delta y. And then on the control volume, we actually want to do this term here. So on each face, we need to keep track of the amount of momentum flowing through it. So that's v rho v dot n hat dA. And you'd go through the same procedure that we did for homework problems. And if you do this properly, what you wind up with is the Navier Stokes equations in 2 dimensions in Cartesian. Okay, I'm not going to go through it here. It literally takes, in a grad class, this takes about a lecture in one half to do. Okay, and so, but you go through the same procedure that we did for conservation of mass. We apply the integral form of the governing equations on these control volumes and this free body diagram. Then the same issue applies. we need to know, we are finding an equation for the point xy, but we need to know the flux of, we need to estimate the flux of momentum that is not at xy, but is at the center point here. And the same goes for the pressure and the shear stress and everything like that. And so how we do that is the exact same way. We use a Taylor series. I'm not going to go through those steps. And then after you apply the Taylor series and you start canceling terms out, then you take the limit as delta x, delta y goes to 0. And then you collect the vector components. And what you wind up with is a vector equation for Newton's second law for a fluid. Okay, and so I'll just write down the final result that we get. So in 2D, we get two components. In general, these are three-dimensional equations, and they just grow longer and longer. Okay, and so in the x direction, or I hat, we have partial rho u partial t, plus partial rho u squared partial x, plus partial rho u v partial y, minus partial p partial x, plus partial tau xx partial x, plus partial tau yx partial y, plus partial or plus rho gx. And recall that here we're defining the gravity vector as equal to gx I hat plus gy j hat. And recall that v equals u I hat plus v j hat. Okay, and now that is the x component of Newton's second law for a fluid in a control volume, a stationary control volume. Then there is a y component, and that equation is similar with the exception that we are now conserving y momentum. So we have the v component here. But other than that, most everything is similar except for the partial x term. Instead of u squared like it is for the x momentum equation, it is uv, and for the y momentum, or the partial y term has v squared instead of uv. Okay, and there are some other other differences with the stress terms too. But in general, it's the same. You're just using different components of either the fluid velocity or the stress tensor or the gravitational vector. Okay, and so this here is conservation of momentum in 2D Cartesian coordinates for a stationary control volume. Okay, and now we're going to work this a little bit, and we can actually, it doesn't look like it, but we can actually get these terms here into a form where we can use the substantial derivative. Okay, and so we will work with this, and so our Navier Stokes equations, we're just going to work with the y direction. But you can do the exact same procedure that I'm going to show you for the x direction. Okay, and so what we'll do is we will first use the product rule on these terms here. So we will use the product rule. Okay, and we will use the product rule, and to do that we will have to assume product rule is that you have to assume that the flow, that basically all of these terms here are smooth and differentiable. Okay, and that's sort of one of those things that's stated in your Calc 1 class, that you can only use the product rule if f times, you can only use the product rule on the function f times g if that function f and g are both differentiable. Unfortunately, in compressible flows, you actually deal with functions that are not differentiable, so you cannot do the step I'm going to do for a general compressive flow with a shock wave. And where you see this is with a shock wave. So here you could have an explosion. and that sends out a shock wave. Okay, and what this shock, and then basically what this shock is, if I was to zoom in on the shock and plot, like say the pressure and X, the pressure would have a discontinuity. So this is where the shock would be. And then also rho would have a similar type of function, and the velocity would also have a similar type of step. And so mathematically, a shock wave is a discontinuity, and across a discontinuity as a shock wave, where both rho and u and v and everything is changing in a stepwise fashion, you cannot use the product rule on these terms. So what I'm going to do is not applicable to these types of flow scenarios. And working with these types of flow scenarios is sort of my research. So dealing with these discontinuities is part of my everyday life, but it takes a lot of getting used to. But yeah, so for this class, you don't need to sort of worry too much about that, but just be cognizant that not all flows that for some flows you cannot use the product rule on this term here. Okay, and that's not because of some crazy thing, some crazy side thing that you learned in Calc 1 and you never dealt with afterwards. This has real world consequences. If you use the product rule on like this term here and apply the resulting equation to an explosion with shock waves, you will get incorrect results. Okay, so now we're going to use the product rule. Then this term, it's going to look like it's going to turn into a gigantic mess. And I'm going to use the product rule. And I'm going to basically use the product rule on one of these v's on all of these terms. And I'm going to basically do what's left. So basically here, I've just split this term into two. So I have v partial rho partial t plus rho partial v plus rho partial v partial t. I use the product rule here, and I use it on v and rho u. I just leave the rho u alone, and the reason I'm doing that will become clear in the next step. So I have v times partial rho u partial x plus rho u times partial v partial x, and then the same thing for basically this term here. I do it on v and the remaining rho v. Okay, and I turn this derivative into this derivative. Okay, again, I'm assuming that these are smooth, and I can actually go from here to here. Okay, if it's smooth, I cannot do this step, and you need to work with the governing equations in this form right here. Okay, so then I'm going to start grouping terms. A lot of these terms have a v multiplying them, and a lot of these terms have a rho multiplying them. So I'm going to gather them up. Okay, and so I have v partial rho partial t plus partial rho u partial x plus partial rho v partial y plus rho times partial v partial t plus u partial v partial x plus v partial y. Well, these terms here should actually look familiar. This equation here, that's just conservation of mass. So this term equals 0 because it's just conservation of mass. So this goes away. 0. That just turns into conservation of mass, which is equal to 0. And this here is nothing more than dv dt, because recall that d of any variable with respect to t into d, Cartesian, equals partial blah partial t plus u partial blah partial x plus v partial blah partial y. And you can see that we have our substantial derivative formula here, where this partial blah is v. So this is really just cap dv cap dt. Okay, so we can show that if and only if the flow is smooth and differentiable, then we can show that this term here turns into nothing more than basically rho times dv dt. And recall that dv dt is just the acceleration in the y component of the acceleration vector of the fluid. So really, this term where basically the acceleration vector is just the x component of the acceleration plus the y component. Okay, so really this is nothing more than mass times acceleration in terms of Newton's second law. Okay, so then we can replace this in the Navier Stokes equations with basically density times the substantial derivative, and we can do the exact same thing for the x component, and we'll get the exact same result, except for that will be rho du dt, not rho dv dt. Okay, so, and you can do the same thing for the x component, and you'll get the same thing, like I said, except for it's du dt, not d rho dt. Then substituting into sub into the Navier Stokes equations, then we get in the I hat direction, we get rho du dt is equal to the sum of the forces, and this is really mass times acceleration. Okay, then for the j hat direction, we get the same thing, except for it's dv dt, and these are forces acting in the y direction, not in the x direction. Okay. So now we need to figure out, we got these shear stresses, and actually the nice thing about these equations is we've made no assumptions on material. So technically, these equations even work for, they not only work for fluids, they also work for solids. So you can put in a solid stress law here, and these Navier Stokes equations these equations here are still valid. And technically, I keep calling them the Navier Stokes equations. Technically, these are called the Cauchy equations. Okay, it's just a little side point. They become Navier Stokes after you substitute in Newton's law of viscosity to describe the viscous stress terms. Okay, but in general, these equations also work for solids. I have a student who's looking at high velocity impact of solids, and we solve these equations here, and we use a stress law for a solid rather than a fluid. Okay. Turns out that the solid mechanics version is actually a bit more difficult than the fluids version. Okay, so now, but recall for now what to do about the shear stress. Now, what we will do is when we use Newton's law, a Newtonian fluid, and we use a stress law for a fluid, after we substitute in that stress law, then these become the Navier Stokes equations. Okay, then these become the Navier Stokes equations. So recall that the shear stress is just the strain rate of the fluid times the viscosity. And so the strain rate is just the deformation rate, and the viscosity is just a property. And recall that really what this comes from, if we have our nice square fluid element and we apply a shearing motion to it, the sides of the stress element are going to rotate. Are going to rotate inwards, and this point here is moving to the right at velocity u, and this point here is moving up at velocity v, and so there is a change, and the strain rate is really related to the rate at which this angle is changing. Alpha and beta are changing with respect to time. Okay, and we argued a sort of simplified version of it, and I'm going to write what the actual stress is in 2 dimensions. So in 2 dimensions, the shear stress on the 2-dimensional element. So we would have tau xy and tau yx. That is equal, these are equal to mu times partial u partial y. This is the shear stress, plus plus partial v partial x. Okay, and so the stress law is a bit more complicated than what we were using way back in chapter 2. But for the flows that you were considering in chapter 2, partial v partial x was basically 0 anyways. So even in those cases, this more general version of viscous stress still produced the same result that you guys were using. Okay, and then this mu here, that is the viscosity, and that is a function of usually a temperature, but if you're dealing with a so-called real gas, it can be a function of pressure too, but it is usually just a function of at most temperature. Okay, and then we need the shear stress in the normal direction. So this would be tau xx and tau xx in this direction over here. And that is equal to twice the viscosity times partial u partial x minus 2/3 mu times the divergence of the velocity. Okay, and basically where this comes from is there is a viscous stress for taking this nice square fluid element, and the stress in the x direction is related to the friction of basically stretching this fluid element out. Okay, and so as the fluid elements basically starts to stretch out in the x direction, there is a shear. Shear is the wrong word, but there is a normal stress associated with that. And you have a very similar term for the viscous stress in the y direction too. Okay, so basically that tells us what to do with the taus. Now, if we assume incompressible flow, this means that the continuity equation becomes the divergence of velocity is equal to 0. We can show, and I'm not going to do this, that if you look at the momentum equations with constant viscosity, what they turn into under this circumstance is rho times the substantial derivative of u minus partial p partial x plus mu times partial squared u partial x squared plus partial squared u partial y squared plus rho gx plus and then that's in the x direction, and we have a y component, and that is very similar. And these are the Navier Stokes equations in 2 dimensions for an incompressible flow with constant viscosity. Okay, and now these are truly Navier Stokes equations here, because these 2 terms come from applying the divergence-free condition, which is the divergence of v is equal to 0, and substituting in the viscous stress into our generic governing conservation of momentum for a fluid element. Okay, and in vector form, we can write this in vector form. This is valid for 2D Cartesian. Actually, I should say Cartesian. Okay, there's a lot of times where Cartesian coordinates don't make sense. That could be if you're doing flow in a round pipe. In that type of configuration, the cylindrical coordinates make a lot more sense. And there are sometimes spherical coordinates make sense in fluid mechanics, like if you're doing geophysical fluids on the flow on the Earth or any other planet for that matter, or a star. For those flows, spherical coordinates actually make more sense often. Okay, so but we can write these equations in vector form, and in vector form, which is valid for basically any, which is basically valid for any coordinate system, is rho times the substantial derivative of the velocity vector minus grad p plus the viscosity times the Laplacian of the velocity vector plus rho g. Okay, and just recall that the Laplacian is the divergence of the gradient of a scalar. And then you also have the constraint that the divergence of the velocity is equal to 0. And so these versions of the Navier Stokes are for incompressible flow with constant viscosity. And a lot of your hydrodynamics flow solvers will solve these versions of the Navier Stokes equations. Okay. Now, if you're dealing with a fully compressible flow, you cannot make any of the simplifications that I just mentioned, and I'll just write them down in vector form, and you have to solve conservation of mass, momentum, and energy together. And so for a fully compressible flow like I deal with on an everyday basis with shock waves, we need to solve conservation of mass, conservation of momentum, which is right here. And in general, it's not divergence free. So we need to actually deal with the entire stress tensor. And this is a vector times a vector. Don't worry about that operator. It's called a dyadic product. So it's neither a cross product nor a dot product. It's a different type of product, which you probably never heard of. So do not worry about it. And if the flow is compressible, basically notice here, we have pressure, we have velocity, and we have density. And so basically we have, in 2 dimensions, we would have basically one equation here, and we'd have 2 more equations here, and those extra equations can give us information on the velocity, u and v components, but also we have pressure. And so we need to relate pressure to the density, but in general, the pressure is a function of temperature and the density. So in other words, for a compressible flow, you also need to do conservation of energy. And I'm not going to show that that control volume. That one gets to be a gigantic mess. But in general, you have to solve conservation of energy too, where essentially you have partial rho E partial T is equal to the divergence of rho V times E plus P over rho is equal to the divergence of this K grad T. This here is called heat conduction term, and you're going to learn about that term in your heat transfer class. This is the viscous work term, and this is the work done to the fluid element due to gravitational work. Where for compressible flows, it is traditional to neglect potential energy. And so this cap E is just the internal energy per unit mass. So it is internal energy plus the kinetic energy. Okay, and then recall that the internal energy, I should really call this, I'll call this E because I don't have anything else to call it. It's just a reference energy plus the integral of CV dt. If the specific heat is not a function of pressure, and for most of your flows that you deal with as an engineer, that is the case. If you're dealing with high pressure liquid rockets, then that is not the case. But for most other applications, you don't need to worry about that. And then also, so basically you could think of now we have an equation that can give us information on density, an equation, equations that can give us information on the velocity vector, and equations that can give us information on the internal energy and thus the temperature. Then if we want to know what the pressure is, we still need an equation of state. And so you need an equation of state, and so you can use the standard ideal gas law. And now these equations look complicated, and they do take a lot of getting used to, but these are solved on an everyday basis on many flow solvers. We solve them in my lab using our own internal computer codes. And some of those computational fluid dynamics techniques, I'm going to go over just the overview to give you a flavor for how they work in the next lecture.